Hello everyone, my name is Yuris Saputra from University of Technology, Sydney, Australia, and today I would like to present our Globecom paper, namely Common Agency-Based Economic Model for Energy Contract in Electric Vehicle Networks. As one of the green solutions, electric vehicles or EV have revolutionized transportation systems thanks to their high energy efficiency and gas emission reduction. According to the Global EV Viewpoint from International Energy Agency, the predicted number of EVs, including battery EVs and also plug-in hybrid EVs worldwide, will rise significantly by more than 3,100% in 2030. This outlook will trigger a plethora of electricity demand for EVs in the power market by up to 1,000% in 2030, and also wide deployment of charging stations for both public and private usages. In particular, as shown in the figure, the number of charging stations increases by 44% in 2018 compared to the one in the previous year. In this case, there are several key main challenges in EV networks, including a plethora of energy demands in the near future that I have explained before in the previous slide. And then we also have a problem when charging stations receive high charging demands from electric vehicles simultaneously during peak hour period, for example, before and after the working time. In this case, the smart grid provider may suffer from a high energy transfer congestion in the distribution network, while the charging station providers may suffer from a high energy transfer cost from the smart grid provider. Even though the charging station provider may reserve energy in advance, however, it's still lack of the mutual economic strategy for energy reservation between the smart grid provider and also the charging station providers due to the selfish nature between them. In this case, in the paper, we propose a new economic model using the contract theory base for charging station providers in EV networks. Our goal is we want to maximize the utilities, or in this case, the profit equally for the smart grid provider and also charging station providers. To concurrently maximize the utilities of both SGP and charging station providers, it is critical to study the strategic self-interest interaction among them. For example, in these two works, both works consider the stackable game, which is there are some interaction between the leader and also the followers. However, both works only work well when the smart grid provider and charging station providers have full information from each other, which is referred to the information symmetry. In practice, smart grid provider and charging station providers usually have some private information, for example, energy capacity and energy demand. This information may not be available for optimization in advance, and those other appropriate economic models should be studied. To address the problems, we can use the contract theory model as one of the promising solutions. The idea of this contract theory is we have the mutual agreements between the principals which offer the contracts and also the agent which accept or reject the contracts. In this way, the principal can maximize the utility under two feasibility contract constraints. First is the individual rationality. The second one is incentive compatibility constraint. The individual rationality, or IR, guarantees that the agents can obtain a non-negative utility during the contract periods. And then for incentive compatibility constraint, the agent can maximize the utility when the appropriate contracts from the principals are applied. There are several works considering the contract theory for their economic models. For example, for these three works, all of them considering a single principal and multi-agent case for the contract theory. However, they don't consider any competition among different principals to attract the agent. In addition, no agreement between the smart grid provider and charging station providers to stabilize energy transfer in the power grid system. To this end, we propose a novel contract-based economic model for EV networks considering a multi-principal and single-agent contract theory, referred to as the common agency contract theory, instead of using a single principal and multi-agent. This multi-principal and single agent can maximize the utilities of the charging station providers and also improve the social welfare of the network. Next, we also formulate the non-cooperative energy contract problem optimization, which allow the charging station provider maximize its utility independently under two common constraints that I have explained before. First is the individual rationality, and the second one is the incentive compatibility from the smart grid provider, and also based under the consideration of other charging station providers contracts using a transformation method. Finally, we propose a solution to solve the non-cooperative energy contract problem using the iterative contract algorithm. In this case, we exploit the best response algorithm to find the equilibrium of the contract solution in the end. Here is the system model in our work. So we consider J number of charging stations belonging to J number of different charging station providers. And then during the EV charging at particular period, each charging station provider has a log file containing the consumed energy to monitor the energy transaction from the electric vehicles that comes to the charging stations. And then based on these energy usage transactions, each charging station provider can send an initial energy contract, in this case, energy demand and also overpayment to the smart grid provider before it can reserve energy in advance. And then using this initial energy contract, the smart grid provider can optimize the charging station provider's contract. And then finally, it can produce the optimal contracts which will be sent back to the charging station providers. In this way, the charging station providers and smart grid provider can maximize their utility individually or independently. Thereby, it improves the social welfare of the AV network. Okay, let's now discuss about the utility function for the smart grid provider. Typically, the smart grid provider has some types which represent the willingness to transfer energy for the charging station providers based on the smart grid provider's energy capacity. For example, if the energy capacity of the SGP is high, so it means that it has the willingness to transfer more energy to the charging station providers. And this type of the SGP is usually a private information that the SGP does not want to share with the charging station providers due to its economic benefit. And then for the utility function, we have the component of satisfaction function, which follows the law of diminishing returns. And we also have the cost function containing the requested energy factor that should be transferred to the charging station provider. And then for the satisfaction function, we have the energy payment factor from the charging station provider and also the energy proportion factor based on its energy capacity. For the utility function of the charging station providers, so actually they cannot know the exact type of the SGP due to its privacy. However, they can observe the distribution of the SGP types based on the public transaction of the SGP in the energy trading market. And then they can also consider all possible types of the SGP to obtain the expected utility. As can be seen in the formula, we also have the gain function and also cost function. The gain function represents the profit that the charging station provider obtain when they serve energy to the electric vehicles, while the cost function here means that the payment that they need to pay to the smart grid providers, considering all possible types of the SGP. To make the contract feasible, we need to satisfy two conditions of the smart grid provider. First, we need to satisfy the individual rationality condition, which is the utility function of the smart grid provider must be equal or greater than its utility level tolerance. In this case, we use the utility level tolerance equals to 0. And then the second one, we need to satisfy the incentive compatibility condition. In this case, the smart grid provider must always obtain the maximum utility if an appropriate contract, in this case the contract designed for that type, is employed. After we design the utility function for both smart grid provider and also charging station providers, so we can formulate the non-cooperative contract problem for both of them. First, this is the optimization problem for smart grid provider to find the optimal energy proportions which maximize the smart grid provider's utility. As shown in the formula, we can see that we want to maximize the utility of the smart grid provider with the constraints of the total actual energy allocation from the charging station providers must not exceed the energy capacity of the smart grid providers. And then the second constraint is the energy proportion for the charging station providers must be between 0 and 1. Then we can formulate the optimization problem for the charging station provider with the aim to find the optimal contracts which maximize the utility independently for each J. As can be seen from this formula, the objective function is we want to maximize the utility of the charging station providers for each J under the constraints of the SGP, including the IR constraints and also IC constraints that we have explained before. Note that we also need to satisfy the condition that the transfer energy must be less than or equal to the energy capacity of the smart grid provider. However, in this IR and IC constraint, we can see that the number of the constraints are too many. To this end, we can reduce the computational complexity of solving the previous problem by reducing the number of IR and IC constraints using an equivalent transformation method in this formula. As can be seen from this formula, the number of IR and IC constraints are now reduced compared to the previous problem. From the previous simplified problem, now we can solve the non-collaborative contract problem using this iterative energy contract algorithm using the following high-level steps. First, we need to find the optimal values of energy proportions which can maximize the utility of the smart grid provider. And then we need to update the possible contracts for each charging station providers to maximize its utility. And then this algorithm will terminate when the differences between the previous and current iterations utilities for all charging station providers reach the optimality tolerance. In this case, the equilibrium contract solution can be achieved. This equilibrium contract solution means that there is no charging station provider which can improve its utility by unilaterally deviating from its optimal contracts. Now we can demonstrate the performance evaluation of our proposed economic model. First, we want to discuss about the validity of the IR and IC conditions. So you can see from the left figure, the IR condition is satisfied because the utility of the SGP always reach the non-negative values. And then for the next figure, the IC condition is also satisfied. As can be seen here that the utility of the SGP for a certain type, for example 2, will always reach the maximum utility when the appropriate contract for that type 2 is used. Then we compare our proposed method with the baseline method in which the CSP only obtains the amount of energy that is proportional to its energy request without using the contract theory. As can be seen from these two figures, the proposed method can improve the actual utility of high demand and low demand charging station providers by up to 48% compared to the baseline method. We also compare our proposed method in terms of the social welfare of the network in the left figure. So from the figure, we can see that our social welfare of the proposed solution can achieve 54% higher than the baseline method. Note that actually our proposed solution can reach less than 10% gap with the cooperative contract, which is referred as the upper bound solution. And then for the next figure, we want to see the performance when the number of charging station providers increases. So we observe that the utility of each charging station provider gets lower as the number of charging station provider increases due to the lower proportion influenced by the limited energy capacity of the smart grid provider. As can be seen here that when a small number of charging station provider is used, so we have 60% higher in terms of the utility compared to the baseline method. And then when the charging station provider numbers get increased, so we can reach the performance utility improvement up to 636% compared to the baseline method. Finally, we can conclude our presentation as follows. In this paper, we develop a new economic model for EV networks, including the common agency-based energy contract model, and then we formulate the problem as the non-cooperative contract optimization, and we also use the transformation method to simplify the formulation. And then we solve the problem using iterative energy contract algorithm to maximize the utility of the charging station provider and improve the social welfare of the EV networks. And then using the simulation, we demonstrate the efficiency of our proposed solution by validify the IR and IC constraints and also evaluate the performance utilities for high and low demand charging station provider and also the social welfare of the network. Thank you for your attention.